Okay, our last video for this week is again sort of about design considerations, and in this case I want to talk about avoiding bias. And there's at least one unique scenario that really only comes up in fMRI that is worth talking through so that you can avoid it. It's relatively easy to avoid, thankfully. And that is a sampling bias. That is the way that we actually collect the data can introduce sensitivity biases in different parts of the brain, and that's something that we need to talk about. Now, there are all sorts of other things that we should talk about more generally in experimental design, but I'm going to assume that you've run across most of them. In this particular case, I want to talk about counterbalancing a little bit, just because it's a problem that comes up that sometimes people are very familiar with, but maybe fail to think it through with respect to fMR. So I'll go through it briefly with you at the end of this video. Let's talk about sampling bias. So when we actually acquire data with fMR, what happens is we don't acquire the whole brain all at once. As I said, it takes normally 2 to 3 seconds to acquire the images from one volume of the head, and then 2 seconds later you have another one, and then etc. In this case, the example on the screen takes 3 seconds. And what that means is that's because we're acquiring it in slices. So we're acquiring one slice, and then 85 milliseconds later, the next slice, etc. And over those 36 slices, it takes the better part of 3 seconds to acquire data from the same part of the brain. 3 seconds later, you're back to the same spot, okay? Because you're here, and then lower, 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 etc. So for instance, if the activation is shown there in red, then what's happening is every 3 seconds, we're acquiring a sample from that part of the brain. And what I've done is I've shown those samples as little circles on the hemodynamic response function. And you can see that if that happens to be the first thing that we acquire, first slice, then we start at time point 0, then 3 seconds later we have a sample. So we start at 0, then at 3 seconds we have a sample, then at 6 seconds, 9, etc. Right? And this is actually a very good sample of this particular hemodynamic response function because it gets the depths and the heights of it. And what's actually happening is you can see in the little graphic here that the slices are being acquired in a descending order. They start at the top, they go down. And if that's the case, then you get this sampling of the hemodynamic, which is fine. On the other hand, if you have a descending order and the area of the brain that you're interested in happens to be at the bottom, then instead of sampling it at 0, 3, 6, 9, now you're going to sample it at like 2.5 seconds, 5.5 seconds, etc. because you're not getting to it until you've gotten to the very bottom of the slices. And if you sample it every 3 seconds, but not starting at 0, then you get a different sampling of the hemodynamic response function, right? So this is at 2.5 seconds, 5.5, 8.5, etc. Now, if this is your only estimate, you've missed this peak. So part of the actual effect size, you've simply not sampled very well because you sampled it at the wrong time. And the only difference between the example here and the example that I gave you before was where in the brain the activation was. If you're doing a descending sequence of acquisition, then you're going to be very sensitive to things at the top and less sensitive to things at the bottom, which is not at all what you want, right? That is a serious problem. Now, that depends on whether or not you're doing a descending or ascending. In this particular case, if you're at the top and you're doing an ascending acquisition, it's the same scenario. You start here, but it's actually the activation that you're interested in is at the top. By the time you get to the top, you've missed the peak activity, and therefore you get smaller effect sizes. Despite the fact the effects haven't changed, you've just sampled them in a bad way. Okay, so the problem comes here when the stimuli that you're actually using to generate the activation are time-locked to the sequence of acquisition. So data acquisition depends on a variable called the TR, or the repetition time. I know that that's backwards, but all of these abbreviations are essentially going to be backwards. I think that's because they were actually originally French, so it was, God, it would have been like temporal repetition or something. I don't know the French. But similarly, you get TR is repetition time, TE is echo time. There's a whole set of examples of these. TA is acquisition time. I don't know why they're all reversed. But the important thing here is that the TR is fixed by the scanner. It's going to try to get through your head as fast as it can, but it's doing it at a fixed rate. And it's not going to speed up or slow down. So every 3 seconds, it'll restart, to acquire a volume of the head. As long as the inner stimulus interval that you have is either the same as the TR or an integer multiple of the TR, so that is to say it's like 2 TRs, then you're going to be in the situation where every time you evoke a hemodynamic response, you're always going to be sampling the hemodynamic response at the same point in time. And that's where it becomes a problem, right? That's what bias sampling is. And that's the thing that we need to avoid. Thankfully, it's very easy to avoid that. And I'll give you the easy way of doing it in just a second. But what happens when it happens, right? By definition, you can only ever undersample the hemodynamic response. You can't get something that samples data that aren't there. So all you can ever do is underestimate an effect size of a condition. However, when you're comparing 2 conditions, that means that it can lead to underestimates or overestimates. So for instance, if the reality is what's shown here on the screen, A is a little bit bigger than B. The red line is bigger than the blue line, right? But I've underestimated A because of sampling bias. Now all of a sudden it doesn't look like there's a difference between A and B because my underestimate means that the difference that should be there is gone. I've underestimated it. However, if I had actually underestimated B instead, now it looks like there's a massive difference between A and B. I have what amounts to a false positive because I've overestimated the difference between them. So despite, this is a little bit counterintuitive, but despite the fact that you can only underestimate any given condition, as soon as you start comparing conditions that could be underestimated, the comparisons can be either correct, underestimates, or overestimates. And there is no way to tell these things apart, right? If you collected the data with this bias, then it's just bad data. There's nothing that can be done to fix it post hoc. So what's important is that we don't collect it incorrectly. That is, we don't ever have our stimulus presentation time locked with our repetition times. Now, that sounds like the kind of thing that should make a big difference for event-related designs where you have events happening, say, every 3 seconds or every 6 seconds. But in fact, it makes a big difference even in a block design. This is an experiment that Dick Veltman did about 20 years ago at this point. And what's really, really interesting is that participants were doing a single task, and the only difference between condition A, B, C, and D is the timing that those stimuli are happening with respect to the acquisition. So those should be 4 bars that are exactly the same. They're doing exactly the same thing, same people, same point in time. The fact that you see a big difference between A, B, C, and D is indicative that even in a block design, where I said earlier that stimulus presentation characteristics are less important, they are, but they're still important. They're not unimportant, right? And you can see here that if you happen to, align them in such a way that you got that C estimate, then there was almost, you got about half the effect size that you possibly could simply due to a sampling bias. So it's a really big thing, and it's a really big effect that we need to take into account. There are multiple ways to handle it, right? One is to do something called oversampling. So that is to say, if you were to have a 3-second TR, which is a kind of a common repetition time, then you could have an inner stimulus interval of 4 seconds. And you can see that an example of that here, so this is the first stimulus that's happening at 2 seconds, the next one's happening at 6, the next one's happening at 10. So those are 4 seconds apart, and the 3 stimulus of the same type. But I've used different colors so that I can signal how you get them on the hemodynamic response function. The TRs are shown here as the start with these up arrows every 3 seconds. And that means that, for instance, we're sampling the hemodynamic response function from the first stimulus, here with these black circles. We've got an underestimate because we missed the peak. The second one happened to hit the peak very well, so we're getting a good sampling. And then the third one is on the seconds in between. Now, what this means is that we've effectively sampled it once a second, right? Because there's that 1 second mismatch between the TR and the inner stimulus interval. And a 1 second sampling of a hemodynamic response function is very good. You get a very unbiased sample at that speed. On the other hand, it still uses a fixed inner stimulus interval. So although this inner stimulus interval of 4 seconds deals with the stimulus acquisition bias, the sampling bias, it would produce terrible efficiency in an event-related design because it's a fixed interstimulus interval. So if you go back 2 videos now to my event-related design video, I suggested that you never want fixed interstimulus intervals on event-related designs. And this is a good example. It solves one problem, but it doesn't solve the efficiency problem. So, as I said, the effect of oversampling is fine, and it works in a block design. However, it absolutely doesn't work in an event-related design, because although it solves the issue of sampling bias, it doesn't deal with the efficiency problem. It makes the evoked responses as small as they possibly can, and as a result, you're just not going to get anything out of your experiment. The alternative is to add temporal jitter. And that was the alternative that worked for event-related designs in terms of improving efficiency, and it's also going to be the thing that works for improving sampling of the hemodynamic response. If instead of locking the stimulus presentation to the TR, you actually have them scattered in time with respect to each other, you're going to get a scattered sampling of the hemodynamic response function, which on average will be unbiased, right? So it may be that any individual sampling is slightly suboptimal, but on average, what you get out of this is an optimal, unbiased sampling of the hemodynamic response function. In other words, by including temporal jitter, so that is to have trials that aren't always a fixed interval apart from one another, they vary in terms of how far apart they are from each other, you not only get away from the problem of biased sampling, you also get away from the problem of the statistical efficiency in an event-related design. So you make them a little bit close to each other, sort of normally somewhere within 4 to 8 seconds mean, with that variance there, and that means that you get a good unbiased sampling of the hemodynamic response, and you have optimal sensitivity to detecting the condition differences that you're interested in. In other words, when in doubt, include temporal jitter. There is no downside to doing it, even if you're in a block design where it's a block, but it's not something like finger tapping where it's kind of just a continuous activity or a flashing checkerboard, but there's actual trials. So in that, for instance, that Arlene Cardillo experiment where there were sentences that were going forward, sentences that are going forward, and then some backward sentences. Those are clear trials. Now, she included temporal jitter between them, so even though it was a block design that's less sensitive to that, specifically to avoid the problem of this biased sampling of the hemodynamic response, even though it matters less in a block design. There is no downside under any circumstance to using temporal jitter. It makes your analysis a little bit more complicated, but it gets away from the major problems associated with event-related designs in fMR. So if you're going to do fMRI, I cannot imagine a scenario where you don't want temporal jitter. The one scenario would be long continuous activation. So if there's something on the screen that's just like flashing continuously for 30 seconds, well then that's an event that takes 30 seconds. It's not that there are multiple sub-events happening every 10 milliseconds or something. Other than that, temporal jitter, it's your friend at all levels. Okay, so that is to say, for both blocked and event-related designs, you always want to avoid the ISI, the interstimulus interval between your trials, being a multiple integer of your TR. The most common mistake is that people make them the same. They have their trials 3 seconds apart and they have a TR of 3 seconds. That is an absolute failure in terms of design, and it means that the data that you get will be poor to meaningless. One way around that for a block design is to use an oversampling, where you still stick with a fixed intertrial interval, but it's just not an interval that's an integer multiple of that. So for instance, if it's a 3 second TR, nothing that's 3, 6, 9, that doesn't work. So it can be 4, it can be 5, it can be 3.2, whatever, as long as it's not an integer multiple of the TR. However, that only is a successful solution for block designs. What you can do instead is include temporal jitter so that on average there's a spread in terms of when the events are happening, and that's going to lead to an unbiased sampling of the hemodynamic response function. It's also going to maximize statistical sensitivity. It also works perfectly well in a block design, and in fact you can then treat your block design essentially as a mixed design where you have events within your blocks and that'll allow you to do things like post hoc sorting of them and saying, well, okay, this person got this one wrong, so I'm going to treat it differently, even though it's within this block, than I would with all the other trials in the block. Okay, so that issue is very much specific to fMRI, and it has to do with the way we acquire the data. But the second issue I want to talk about, really counterbalancing, it is not specific to fMRI at all. This is relevant to any experimental design, and it's an issue that comes up, with the vast majority of experiments. Somehow, it sometimes gets overlooked in fMRI, which is why I'm going to sort of mention it now and not some of the other things that also come up with good experimental design. And the key here is that the order of tasks or the order of the stimuli can influence the results. So in order to get away from the fact that you may have an idiosyncratic order that gives you a result that's interesting or not interesting, but is specific to this particular ordering, you need to balance the order across the runs, okay? So that is to say, if you have people doing one 10-minute experiment, then they can't all of your participants can't do it all the items in the same order. Because that way you never really know whether the thing that's of interest is your activation versus baseline, or whether it was driven by the fact that somehow there was some learning that happened over those 10 minutes, and because it was all in the same order, you got exactly the same effect, but you didn't really test the possibility that it was this artifact rather than the thing that's of interest. Okay, so this comes up with unbalanced runs all the time. So imagine that I'm interested in working memory, and I was going to use what's called an n-back task. So this is a classic working memory task, and what happens is I give people stimuli, and in a one-back version, I just ask them to push a button anytime a stimulus repeats. That is, the one back was the same as the one that you just saw. So you see a repetition, you push a button. In that case, there's a very simple working memory component, because I just need to bear in mind what the last picture was, or the last word was, and as soon as I see a repetition, I push a button. A more complicated version of an n-back task would be a two-back task, where it's not the last one, but the one before that that's really relevant to me. So I need to keep two items in memory, and therefore there's more of a memory burden as I go. So it's not a repetition, it's a repetition with one in between. Okay, and you can do the same with a 3-back or a 4-back, and you make the memory task harder and harder as you go. So if I had this idea that I wanted to work on working memory, that was what I was really interested in, and I was just going to have people do 1-back, 2-back, and 3-back tasks with the idea that, the working memory component gets harder each time, so if I continue to see increases in activation, those are parts of the brain that are likely to be involved in working memory. But then let's just say I have a 1-back task, and they do it for 5 minutes, and then they do a 2-back task, and then they do a 3-back task. Okay, so there's now an order compound. Everybody started with the easy task, they went to the middle task, and then went to the harder task. And we don't know now whether or not we're accurately seeing the differences between them, because it's confounded with learning. So for instance, during the 1-back task, I got familiar with the paradigm, and it was actually harder than it would have been normally because I hadn't had any practice before. So 1-back was the first thing I found, and it was harder than it should have been. By the time I get to 3-back, that's easier than it would have been because I've had practice with 1-back and 2-back. So what you need to do here is counterbalance the order across participants in a way that avoids this dependency on these kind of linear orderings. One way to do it is just rotate the order. So that is to say, let's just say I had 21 participants. I could have 7 of them do 1-back, 2-back, and then 3-back. And then I could have another 7 do 2-back, 3-back, and then 1-back. So you can see I've just rotated it. And then the last 7 I can have do 3, 1, and 2. So again, I've rotated again. And you can sort of see that in the illustration here. There's a cycle, and people start either at 1, or they start at 2, or they start at 3, but then they follow the rest of the cycle. That's good, right? We could definitely do that. And then the number of orderings tells us the number of participants we have. We have to have an integer number of those. So for instance, in this case, there are 3 orders. And therefore, I need to have some multiple of 3 subjects, because if I don't, then it's unbalanced. On the other hand, this isn't optimal because the transitions are always the same. That is to say, 2 always comes after 1, 3 always comes back after 2, and 1 comes back after 3. So if it matters that the transitions are important, so if 3 always follows 2, maybe then that does indicate that there's too much learning that's taken place. So we have to avoid that. Then we need to think about using something a little bit more complicated to avoid biased transitions. That is, the transitions from one condition to another. For that, the correct answer, the full answer, is to use something called a Latin square design. And I don't really want to go into this in any great depth because it becomes a combinatorics discussion. But let's just say that for the example that I've given, where there are 3 conditions, there are 6 orderings that are unique. And I've listed them there. 1, 2, 3, 2, 1, 3, 3, 1, 2, 1, 3, 2, 2, 3, 1, 3, 2, 1. And I've tried to draw out, like if you start with 1, you have 2 options. You can go from 1 to 2 or 3. And if you go from 2, then you have to go to 3. And if you've gone from 3, then you have to go to 2. So that's how you get those 6 orderings, right? And there are fairly straightforward sort of ways of doing this for n conditions. It becomes a little bit more complicated because it uses a factorial, which is just the size of the conditions increases dramatically over time. But look, if you have 6 balanced runs now my number of subjects needs to be an integer multiple of 6 rather than 3 from before. And the advantage to that is it avoids this biased transition. The disadvantage is I need an enormous number of participants. So if I have 6 conditions, let's just say, to be fair, I want a minimum of like 10 people in each condition just to make sure that we're getting some kind of decent sample. And that's probably too small, frankly. We're already talking about 60 people for a basic, simple experiment. If you had 4 conditions, you're talking about 24 orderings. And at that point, 10 each, you're talking about 240 people in your experiment. So Latin square designs are theoretically optimal. And in small number of conditions, they're an excellent way to go forward because they avoid both order effects and transition effects. However, in real-world experiments where you have basically more than 3 conditions, they tend to be impractical, and you have to get away with something like an ordering, counterbalancing the ordering. Now, it's worth sort of pointing out here that this is pretty easily and sensible in a block design, because you can imagine how you would repeat blocks of tasks. But in an event-related design, by definition, if you include temporal jitter, there's a different order of these events. You want to make sure that you don't have one order that applies to all participants, because you could unluckily have ordering effects or transition effects as part of that. So you want more than one version of your experiment where the events themselves have been randomly reordered and you've redone the temporal jittering so that across participants it's balanced. So this is another key aspect that sometimes gets lost in fMRI. And this is what I mean by it's an important design characteristic for experiments in general, but sometimes it gets forgotten in fMR because people are so worried about sensitivity and avoiding, for instance, sampling bias, that they come up with their delightful event-related design with a particular ordering that they like, and then they just run it. And they forgot that at that point they've introduced counterbalancing ordering biases. You need at least 2, but possibly quite a bit more than 2 orderings to avoid this potential issue of ordering of trials and the ordering of the transitions between trials. Like, one thing that some groups do, which is perfectly sensible, is if you have a complicated design where you have, say, 3 or 4 conditions, given that you're never going to be testing 240 subjects, or it seems very unlikely anyway, what they do is they generate each data acquisition sequence randomly per subject. So on average, you have, say, 20 samples out of 240 that you would really want, but they were done they were done in an unbiased way, and when you combine them together, the likelihood of having order transitions or order effects in there is extremely small to occur by chance. So that's one solution. An alternative solution is to just have multiple versions of your experiment with different timings, different orderings randomly, so that on average these effects wash out. Okay. So with respect to counterbalancing, then the Latin squared approach is the optimal, but it's really only practical for a really small n, where n is the number of conditions. 2 conditions, practical. 3 is on the edge, 4 is right out, and beyond that, forget it. So in that case, it may be sufficient to do some sort of rotation of conditions where you have a large number of conditions. So you rotate the order of those conditions across participants so that you have an unbiased ordering. You still have biased transitions, but maybe that's less of a concern for you. If you're doing something with an event-related design, normally what you end up doing is creating these kind of pseudo-random orders. That is to say, you come up with a random sampling of time intervals and ordering, and that becomes your one run. And you can repeat that over subjects, but you don't want to repeat that over all of them. You want to have multiple pseudo-random orderings such that on average across participants, you get rid of any of the ordering effects that may have occurred by chance. Okay, so this week had a lot of information, and this is the end of the fourth lecture for this week. So I just want to summarize some of the things that I hope that you've taken out of it. One is that block designs are the most sensitive, most statistically sensitive, and they're best because they maximize the effect sizes that we're trying to measure. The way you maximize that in terms of maximizing signal to noise is making sure that your block lengths are in this 16 to 45 seconds time window, and you're alternating blocks, many short blocks rather than long blocks where the noise would start to interfere. Event-related designs are maximally flexible, but they're much less statistically sensitive. That is to say, you need to collect more data because the effect sizes that you're measuring are smaller. Anytime you use an event-related design, you need to include temporal jitter. And as long as you have more than an event versus rest, so you have, say, 2 different types of events or 3 different conditions, whatever, then you need to make sure that on average, the temporal jitter means that the events are separated by somewhere in the 4 to 8 seconds on average. Absolutely no fixed interstimulus intervals. Whenever you're designing an experiment, whether it's a block design, an event-related design, a mixed design, the baseline choice is absolutely as essential as your activation choices, right? And that's because what you're measuring is this relative effect. It's the difference between your activation task and the baseline. So if you don't take the baseline seriously, you're still comparing between 2 things, but one of them is a bit ill-defined. What I always recommend with respect to baselines is that if you can design a high-level baseline, go ahead, go for it. But do yourself a favor and include a low-level baseline like rest or fixation or something that's very different from your activation task as well, just in case something like pure insertion or implicit processing happens and you get caught out and discover that your activation task and your baseline are actually giving you the same things when that wasn't what you expected. And then finally, there are just a few things that you want to avoid anytime you design an MRI experiment. One is you want to avoid temporal correlation in events. If you're interested in the event structure of a trial, make sure that you build temporal jitter into the nature of each trial so that you can separate out different parts from each other. Always avoid making sure that the inner stimulus interval, the time difference between trials, is either the TR or it's a multiple of the TR. You don't want an integer multiple. So don't have events that are 3 seconds apart or 6 seconds apart, etc. And then finally, make sure that you're not doing a single order of events across all participants. You do need to worry about counterbalancing, and it does make a difference because it can introduce all sorts of biases that you couldn't tell unless you had collected the data using multiple different orders. That could be counterbalancing the orders in block design through a rotation. It could be using a Latin square design, or it could be that you have multiple versions of pseudo-randomized event series in an event-related or a mixed block event-related design. Any of those is a reasonable solution, but be sure that you include at least one of them. And as always, this is a suggested reading list. I would very much encourage you to read Chapter 9 of Huddleston and McCarthy. But in addition, there are a number of the papers that I've talked about this week that are here. And every one of these papers are papers that have been really fundamental to the field, and I would recommend them very highly.